Joy. I want to print outputs. These are the weights. I can start with printing the weights maybe. Weights and output and loss, yeah. It's not the same, is it? We start with this as the first element of the weights. No, it is already the second. Okay, so the second one is that one. It's already different. Hugely different, I would say. You see how in this case it hardly changes. Hardly changes. Maybe alpha's wrong. Okay, alpha is 5 times smaller. Let's put this one at 5. Let's print a neural network before we do a forward pass. No, that should not make a difference. Actually, I'm already printing it here. I should be printing that. That's the initial value. Huh? Oh, it's called rounded off. Then you got up. That's the initial value. $305,205. Now here it prints here this prints as a double. I think the precision is maybe just too low. Could set the precision at 8 and then we have the right thing here. Super unclear. Oh, I'm confused. Well, this prints it with a precision of 8, it seems. I'll set this one to 8 as well then. Complete set at 9, it seems. Now we're talking, except for the last one. The hell? That one is the same. Oh, that's also not the same. 1, 2, 3, 4, 8. 1, 2, 3. Now it prints 9. 1, 2, 3, 4. This one prints 8 and then it prints 9 anyway. 1, 2, 3, 4, 5, 6, 7, 8, 9. Why is it printing 9 suddenly? Ugh. Mm-hmm. Finally, we have them printing the same thing. So then the TensorFlow calculates I think this is the loss with the initial values and the output with the initial values. Yep. And the loss. So they completely agree. And then the updated weight is, we get a C and a delta, and we get a gradient, and we get a Y value. That would be the first weight. And that is that value. Well, that one is correct then. But this one isn't. I is not the same thing. 3350 and here's this 45. Nope, they're not the same thing. Why not? Okay, and next one is also the same. Wow. This one also the same. And that one not the same. But pretty much so. 3, yeah, almost the same. It's also not very far off, it seems. That's actually exactly the same now. This one. Yeah, this one is not. It is 8, 4, 4, 5, 2, 4, 8, 3. Only this part is the same. Well, for 6 or 7 digits, it's not too bad at all. And this one also shows the output, so I'll probably want to add output to this output, neural network. Let's print the output after the forward pass. I think I can just add outputs here. What is output? Output should be output is totally a thing. Output is the result of the sigmoid. Also two-dimensional, I think. Did I get this one right? Well, 0 there, then it means it's just a one-dimensional thingy. It should be, but I don't know what the shape is actually of outputs. This one is 1x batch size. Maybe this one too. Well, at least printing it once. Output. See, it's not printed at all. Come on. Outputs. Oh, it's a 1.9. Okay. I don't know why it prints it like that. It is printing the outputs. So compare that with this one. That output, the last one, is no, 2866. It's not that bad. It's not exactly the same, but close enough. Oh, this one is... Oh no, that's that one. I was looking here. Yeah, okay. So I think I have a program that kind of proves that it works. Because I wrote a second implementation. I'll show you how this looks like. So it's based on my quick hack layer and tensor and whatever. I wrote the classes for that. So I create a layer here with 2 inputs, 1 output, and a batch size of 9. I'm using this a neural network. That's a single neuron, right? Because it's a single layer and it has a single output, so it's a single neuron. Now we set weights for the weight for the input 1 and input 2, and that's the bias. And then we have as input, we have 2 inputs. So one is just runs from 9 to from 0 till 8, and the other one is listed here, which you can see is more or less a straight line going from -4, -1, +1, 2, 5, 8, 10, 12, so just a line like that going up. I saw that as the Y value, or X1. So S stands for sample of the batch. Got 9 of them. Target output is this list of random zeros and ones. And then we do 5 steps. A forward pass, and then we calculate the loss, which is the mean square error, I think. So difference between this one and that one, and then the difference squared, and then summed up, and then the means divided by the number of them. And then we do calculate the derivative of the MSE for the same inputs, that value, and then we do a back propagation. If we had more than one layer, then I could repeat this last call. Go from layer to layer, just passing the side that we get back to the next one. And then of course taking different layers. Previous layer, but now n is just one layer. So I just call back propagate on it directly. Yeah. No, that's hardly anything to see here. Might better look into, for example, the back propagate looks like this. I'll make a matrix delta and xi. We fill in the delta. So this is just, you know, a C++ hack. Delta is a matrix, so it has it has a rows and a column. This is the row and this is the column. But I just do everything per element. So the number of the rows run over all the outputs, and that is exactly one output at this point. And as over the samples, so that's 9 of them. And then they take the xi of that times the output that belongs to that times 1 minus the output. That's the initial xi value. It's not true. The initial xi value is passed here. So we use the initial one and then we calculate the delta here, sorry. And then we calculate the next xi, which is returned in the end. Yeah, I don't know. It's not that complex. It only took me 2 weeks to figure it out, but in the end it's less than a page of code. Bottom line being, of course, that this is just a double. Everything is a double here. It's just this double becomes that double times that double times that double, or float, whatever. Float type is currently set to float, not double. But it does mimic the same thing as my TensorFlow-based neural network, which just looks like this. Yeah, that's way bigger. Scroll, scroll, scroll. TensorFlow wants you to create a scope. Debug output. Operations that we need to run. The initialization. And then again, just 2 inputs and 1 output, and this is going to be 9. Now we define a placeholder for the inputs and the labels. Let's see, zeros and ones, target, and a weights bias matrix. This declaration, it's not really connected or filled in or anything yet. This defines an operation that we have to execute later on, so I'm pushing it to the vector, so it will be executed. The operation is assign to weights bias some random numbers. Also give it the shape of the thing. And we get the batch size, which is dynamic, so we have to do it during runtime. You get this shape of the inputs thing, and then slice apparently gets the last size of the last dimension of it, which is the batch size. And that's a scalar, I guess. And inputs 1 is the same as inputs, but then with a lot of ones, so that we can put bias into the weights matrix. So add ones to the input. Yeah, another constant that we need. The forward propagation is still quite short, I guess. So you multiply the weights bias matrix with the inputs with the 1. So the 1 gets multiplied with the bias and then added. Just during a normal matrix multiplication. So then you get weight times input plus weight times input plus 1 times the bias. And then we take the sigmoid of that, and that is those are our outputs. Residual is then a subtract operation, but outputs minus the labels. Labels are our targets. The loss function is not really needed, so I define and print it here, but no. What we do want is to know the derivative. So if this thing is, if the loss is 0, then the derivative will also be 0, because it's a square root. It's a sum of a square roots. The only way to become 0 is when you are in a flat bottom, the bottom of a pit somewhere. So a loss of 0 means that the slope has become 0 as well. You cannot go deeper, so there is no slope. So the deepest point will have a derivative or a gradient of 0 as well. And that's what we use, the gradient of the loss. So then backwards propagation. Calculate the xi, which is just 2 times the initial xi is 2 times the residual, so the difference between output and target. And that's the well, almost, yeah, that's the derivative. Partial derivative, actually, it's still a vector. And here's the derivative of the activation function. And then we multiply those two to get the delta, whatever delta is now, mysterious delta. And then from that, with another matrix multiplication, and a transpose even, calculate the gradient, multiplied with the learning rate to get something called dg. I don't know what the D stands for. The G was gradient, and the D is probably delta or something. But I didn't want to write delta. I don't know. I hate abbreviations, but this one slipped in. And then, yeah, dg is just going to be subtracted from the weights. I guess that happens here. Where's my sub? Yeah, assign sub. Assign sub, yeah. So weights becomes weights minus dg. Yeah, that's the whole backpropagation. So this did build up a graph that didn't calculate anything, but now we have defined a graph which is stored in the scope variable, and I think also in the session, or not yet. Here I just C++ program fill in inputs and training values. Yeah, the scope is passed to the session here. So here, create a session, we pass the scope to. And then the client session also knows the graph that it has to execute. And there we go, run it. Now the first time we only pass run operations, so it doesn't really care about anything but the nodes in the graph that are part of this vector, the run operations vector. In other words, the only thing it will do here is fill the weights bias matrix with the run values. And then we run the thing for real, which means that it's doing a single forward and a single backward, so a single forward pass and back propagation. And then we start training it. That is, the weights were updated also. So we run it again, exact same thing. Where's the running? Yeah. Just keep running it over and over, the same thing. TensorFlow figures out what it has to run based on input and output, the demands that you have here. So the actual outputs that we are running end up in this vector, but what we want to read, which tensors we want to read, are stored in the fetch outputs. So the only thing I'm interested in here is the updated weights bias and the outputs of the neural network, because I want to print it. This one is important. If I do not ask for updated weights bias, then it's not going to calculate it, and not calculating it means that the weights bias is not updated. So then you can loop whatever you want, but nothing changes. So you really have to ask for that one. The weird thing, however, is that it still wants me to do the input. So let's have a look at the graph. Run this thing, it tells me what to do. Well, using some Python there. So the program is dumping the graph, and now I use Python to make it into a picture. I think this one. What were we going to look at? Oh yeah, so if the first time, of course, we have inputs, and I need to pass them, feed them into the network, because they are used. Well, for example, I use it to get the batch size. I feed not in a matrix, I think, into it that has a dimension 2 times 9. So it can get the 9 from that because I feed it into it. Say, oh, it's a batch size is 9. Okay. Then it makes a vector of size 9 and it fills that with ones. And then that's added to the inputs. So now we have a variable called inputs1, which is just inputs with a 1 added to it. However, the second time that I run this, I don't need inputs anymore. I have inputs1, which is not changing. It just should be still there, I think. So the second time I run, the only thing that has changed is the weights here. This thing has changed. And therefore, we have to recalculate the output of this matrix multiplication, which means that we need this input here, which means that we need inputs 1. But that was already calculated last time. So I really don't understand why it asks me to supply inputs again. Not just inputs, but also labels. Same thing. Labels are inputs here. Now, the first time what we do with the labels is... okay, labels are needed actually. You know, this thing was changing weights, therefore this is changing, the output of the sigmoid is changing, and then we subtract labels from that. So it needs labels to calculate the residual that continuously changes. So I might understand that one. Now, yeah, and the rest is built on top of that. Then, except of course, yeah, the loss function, I never use it. So this is just a leaf branch here of the graph that they might as well get rid of, because it's calculated because I take the identity of it, which is then being used to print it as debug output. Now, if you consider inputs 1 to already exist, then of course the transpose also already exists. Now, maybe it's using too much memory. Maybe it throws this away and then recalculates it every time so that it doesn't have to store it. But I really see no reason why it would recalculate inputs 1 every time over and over again. Okay, so these two together make bit size times g, and then we multiply that here with the rate, and then we get alpha times g, and that is then subtracted from the weights, and then we go again. So that's how it works. But if I do not pass input, I think all hell will break loose. Let's see how we can do that. I have an input feeds here. Inputs feed, which is this thing. Let's make a new one. We'll give it a new name, input feeds 2. And I'm only passing labels because that might be needed, but inputs, really, no. I don't believe it. Maybe what I should do is get the result of input 1 and then feed that back into it. But yeah, that would still be slow, because then I read it to this from the GPU to the CPU, and then feed it back into the CPU again, GPU again. Well, it never changes. I mean, during this learning loop, so I don't like it. It's the only place where I use it. I'll make that as 2. So now I only feed in the labels and not the inputs, because I should already have that. But yeah, then it's going to tell me you must feed a value for placeholder inputs. So it really wants me to feed the same inputs over and over and over, and I don't get that. Well, not only don't get that, I really don't like it. I mean, now of course there's nothing, but imagine wanting to learn from a batch of 1,000 images, and every image is 100 kilobyte. That's 100 megabytes of data, which doesn't change. Please keep it in the GPU on the video card. Don't ask me to upload it every time. How can we find information about that? I can ask ChatGPT, but yeah, the thing has become more and more stupid, it seems. It knows Python quite well, so maybe I just ask it the same question, but then for Python. And then maybe it will tell me something sensible. Let's start a new chat. Using TensorFlow while training a neural network. Is it necessary to feed the input training data into a session run every time you do well do the next pass. I'll keep it short. This inputs. I think this is the target. And here we have the feed thing that mentions X and Y explicitly. This is so tiresome. The thing is so stupid. This. That's what we want. So I need a persistent tensor for input 1, and maybe even for labels. Then use some cross. You can create a persistent tensor by defining a TensorFlow variable or a constant tensor in GPU memory. Oh. Two persistent tensors with caching. If you're using TF data API, you can cache your data set in memory of the loading at once. This is especially useful if your pre-processing steps are computational expensive. Such don't understand that. Let's put it that way. You can use the cache method in TF data pipeline. I think it derailed again. Okay, so it's just a load of bullshit. Blah 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 blah. Basically, this means I don't know. I'm better with Python. That's my translation of that. A linear that comes back, a paragraph that comes back over and over and over and over. There's absolutely nothing persistent about this, of course. Nothing. Nope. I'll have to Google it, I think. TensorFlow, C++, persistent tensors. You need to create a tensor, word type shape, creating a TensorFlow, blah. Where's the word persistent? Not enough persistence there. Persistent. Did I write that correctly? Persistent. Persistent C++ object. What? 2 months. C++ tensor library. It's not using TensorFlow, but hey. Looks like the same guy. Yeah, exactly the same post even. Let's be distracted. Does that even compile? Probably means plus B. So I guess he typed it in without testing it. interesting. And then it was dead. No commits since, well, the post was 2 months ago. Did it expire? I didn't pay attention here. What happened? It did expire, didn't it? Invalid, yep. So useless. Right. I think I'm going to eat. Okay, I'll be honest. I want to open my email client. You never know what happens when you do that. So I have to stop the stream. I don't think I can open it on a different monitor. Maybe I will do it here. Okay, I'm just going to try. Launch. Yeah, that works. Okay, compose to this guy here. Provide link on your GitHub README is expired. Hopefully you'll find some C++ interested guys there, at the very least. I'm going to continue searching, I think. Yep, maybe all variables are persistent. It's just an idea. These are just operators. Yep, every variable is persistent. Attributes. Do we have any attributes there? Hello, attributes. Anyone? No, I don't see any attributes. What the hell? Why? Maybe attributes are only for operations. Attributes. There. Excuse me. No, they leave you to guessing. They leave you guessing. Yeah, we are going to guess. Maybe the problem is then that so my weights bias is a variable, but the other ones are placeholders. Placeholders need to be fed in. That's no problem, but then I don't have any other variables. And if variables are the thing that I need to be persistent, then maybe I should just make my input 1 a variable. For example, if I make input 1 a variable, then I definitely should not be have to feed inputs into it again. But if it's a variable, you need an assign. So what I could do is I don't see the problem really. Let me commit what I have now because I'm just going to. Persistent inputs one variable. So I'm going to call that a variable. Variable, where's my input one? Yep. And then the thing has a name. And I guess this is the shape. And then of course float. What is the shape of my inputs one? That's just the same as inputs, I guess, but then plus one. Let's see, inputs. Placeholder shape. No. It's an unknown rank. Is that even possible then? I don't know if that's going to work. Anyway, one larger inputs. That's all plus one there. Float. Yep. So I do have a batch size here already. So now, during runtime, we know how big this thing is. But maybe just works all by itself. I'm going to call this temp inputs one. So what I want is an assignment, and the assignment then must be executed. It's just an operator. Let's just do assign. Assign scope. We assign to my variable, which is this, from temp inputs. Why would that not work, right? Especially since input one is undefined until this happens, so I can just do a debug show for inputs one. This is a temp. Show the temp on temp. See, now I have a inputs one is a variable, and then assign it to input one, and then later on we use input one, just like that. Here again. Transpose of input one. No, I don't know. It's step one. Does it compile at all? Nope, not running. Invalid argument. The shape is not fully defined. So that was not possible, I guess. But what exactly is not possible? Add a few lines here. I think this is already failing. Okay, so I'm gonna call this one foo. And then we're going to call this one what it was. Do now I have the same code that I had, but this line is extra, I think. Yep. So if this fails, then this line fails. And probably that's the one that fails, because it just has to be known when making a variable. Amazingly enough, it's not the case. Yeah, maybe it's just not doing anything with it, but okay. Yeah, I'm going to eat, guys.